Okay, Gloriana, what do you have to say?
My bad, Eric.
Probably not. Okay. Okay. So all we're doing is just going from one pressure to another, right? And we're just looking at points on that phase diagram between the liquid-solid boundary. How do you get them from one to the other? Okay. So from one pressure and one temperature to another pressure and another temperature. The liquid-vapor boundary in the phase diagram. Now just the Clapeyron equation. So, and I think we did this in the concept preview too, didn't we?
Yeah.
Went from here to there. Okay. So again, different temperatures and pressures to their new temperatures and pressures. That boundary in the phase diagram between liquid and vapor. Okay. I already talked about that. I think that's good enough. Okay. Let's go ahead and jump into this. The vapor pressure of dichloromethane at 24.1 degrees Celsius is 400 torr. Enthalpy of vaporization is 28.7. Estimate the temperature at which its vapor pressure is 500 torr. So it sounds like yeah, that's what I'm thinking too. Clapeyron, right? Because they told us the vapor pressure at this pressure and that temperature, and they told us the enthalpy of vaporization. So do we have everything we need to use that? Where's my book? Yeah, that's what I'm thinking about. What about that volume question?
You don't need volume. You just use H that P2 equals P to the negative H back over R times 1 over T2 minus 1 over T1.
Oh, we were looking at the wrong one, Melissa, right? Because we're talking about the one that has volume in it is solid-liquid boundary, right? This is liquid to vapor. No wonder, man, I was wondering, well, how the hell are we going to do that? This is liquid to vapor. So this is Clapeyron, not Clapeyron. So don't we have everything we need then? We'll just solve in the Clapeyron equation. What symbol are you going to solve for?
T2?
T2, exactly. I would solve for T2. Find T2. Let's make sure everyone's on the same page here. What is it? So we derived this. Know how to do that. I'm just copying it from the notes here. P1 e to the delta vap H over R
Yeah, I know, yeah. That's freaking out.
So do we have to, are you going to mess with converting these torrs to pascals?
Yes.
Kind of wasting your time if you are.
Aren't you supposed to?
Oh no,
Because
dividing it.
it depends on the situation, I think. But in this situation, when you bring the P1 over to the other side, those units cancel out. So when you go with that work of converting to pascals, that conversion factor would cancel out too. So just make them consistent.
I got you.
I would just be careful with this kilojoules and R.
So 500.
That's not consistent.
Sheldon. Why can't you in the back of the book for 6
So did you want to finish it or go on to the next one?
Next one.
So everyone sees what to do for this first one? Kelly, you see what to do? Jeff, you got it? All right. All right, let's go on to the next one now. The molar volume of a certain liquid is 161 cubic centimeters per mole. At 1 atmosphere and 370, 50 Kelvin or something. Alyssa, you read the question. Why should I read it? You read it.
Why?
Because you sound like you want to talk so much.
Everybody can read it themselves.
Oh, read it out loud.
Wait. For 6.1, do we need to change the kilojoules to joules?
Yes. Otherwise, it won't cancel if they are. Right? Okay. Yeah, just read it. Thank you, Alyssa.
The molar volume of a certain solid is 161.0 centimeters cubed moles inverse. At 1 atm and 350.75 Kelvin, its melting temperature, the molar volume of the liquid at this temperature and pressure is 163.3 centimeters cubed moles inverse. At 100 atm, the melting temperature changes to 351.26 Kelvin. Calculate the enthalpy and entropy of the fusion of the solid.
Okay. So Mel, now what? Well, I thought we were going to move on to this one.
Well, this one is you have to use dP over dt equals delta S transition over delta S transition V.
Okay, I hear a suggestion. dP over dt equals, what was that relation? The change in entropy over?
Clapeyron equation.
Yeah, over delta S. Oh, delta, yeah, delta V.
All right.
And then you move the delta V over.
So which part are you looking for? Are you looking for enthalpy or entropy? We have to find both of these.
I'm looking for entropy first, and then you use delta S equals delta H over delta T to find enthalpy.
Yeah. So for the,
For entropy,
I agree. I think you're going to have to mess with this one to get entropy, because that has delta S in it. But how about the enthalpy one?
yeah, and then on chapter 4, the change in delta S equals delta H over delta T. So you just move the delta T over once you get delta S and you get delta H. And you just write the subscript fusion on all.
Okay. But this one didn't, this is the one where we integrated and we got our concept preview question, right? So isn't that just the Clapeyron equation?
That P plus P1 plus, yeah.
Right? P2. Yeah, this is from our concept preview. And they call it the Clapeyron equation. P2, I'm just copying it again. P1 plus delta fuse H So let's just look at one of these at a time here. Let's look at, let's look at enthalpy first. All right, so you took this expression, we substituted in the concept preview, and then we did some integration, and we ended up with this expression. How do you get enthalpy out of this? How are we going to solve for that enthalpy? What would you do first? Do we know the pressures?
Yeah, 1 in 100.
Yeah, and then now the units need to be what? In pascals. Because notice how we're plussing and subtracting and things here. So now that had better be in pascals. So we know what these are. What are you going to use for T2 and T1? We have those? Yeah, we have those. Okay, how do we handle, or how should we handle this? The change in volume.
The difference, and then you have to convert it to meters cubed.
Yeah. It's just what Shelby said. I agree with that. It's just the difference. And then convert it to cubic meters. So that per mole part will cancel with the per mole and the enthalpy of the fusion. So it's just the difference. Now, when you find difference, it's always one minus the other. And either you're going to have a positive or negative answer. When you find that delta V, you take which one minus which one. Which one would you do? That's what I'm thinking, because it's melting. So you're going from solid to liquid. So it should be final minus initial. It should be the liquid minus the solid. That's what I agree with that. So do you end up with a negative number for that? Because that could screw you up.
No, it's positive.
Oh, it's positive?
Yeah.
Okay. But I would just watch that, because I think one of these homework questions, that's where I screwed up. Okay, so we have an idea how to get the enthalpy of the fusion, right? Okay. Now, Kevin was guiding us here to get entropy. Okay, so he said he started here, but now what would you do? And the idea is to get entropy. I think we're going to have to integrate.
Once you get the enthalpy, can't you just find the entropy while using delta S equals delta H over delta V? And in this case, you'd be using the delta T of fusion, which is 350.75 Kelvin.
I wonder if that would work. Because what I did, that's really interesting. I used to try that. Did you get an answer doing it that way?
Yeah, I did. I got 15,860.
Because what I did, I wasn't so sure I could do. This is what I did. Delta S over delta V. So I integrated. I had delta S over delta V dt. Then I integrated. And I pulled, and this is what I wasn't so sure I could do. I pulled this out of the integral. So then all I ended up with was P2 minus P1 on that side equals delta S over delta V. I would be interested if we got the same answer. And then T2 minus T1 on this side. So we know what pretty much everything is. We know what all these guys are.
Yeah, that's what I was thinking.
And then solve for delta S. But you used the enthalpy in there, right?
What are we solving for?
They want entropy.
I'm confused.
They want entropy.
Yeah, I did that, and I got 45.23 joules over mole per Kelvin.
So could we just take delta H over T and be done with it. That's what I'm wondering.
That's what I'm saying. I did that for enthalpy. Once I got delta F, I just multiplied it times the temperature of fusion, which in this case was 350 because it was melting.
Yeah, did that work?
I got the H, which was 15,867.5 joules per mole.
Yeah, you got numbers. I don't know if it's right or not. Let's check out the back of the book, though.
So I have the back of the
I'm pretty sure this way works.
What'd you get?
I'm pretty sure this
H
works.
for enthalpy is 15,867.
I'm pretty sure I got the back of the book answer with this way.
16 kilojoules, basically?
Yeah.
Okay.
And then for delta S is 45.23 joules.
Oh, it's easier. You got an easier way. All right. So you don't have to do this whole integration stuff. So did we totally confuse you on how to do number 2?
This one?
Yeah, that's what
Oh,
yeah,
never mind,
that's
sorry.
what it is. And then I
This is
Oh, this one, yeah,
H
yeah,
rewrote it to
yeah.
delta H.
yeah.
Okay. I don't know if we use that yet. Let's see if it'll type it in.
Because it says it's melting.
That's two of them.
No. It says
Oh,
that
the
the melting
fusion is
temperature
nice.
temperature changes.
I don't think that's the same fusion as
So let's let you get caught up, and then we'll talk about number 4.
Right, Dr. Smith, at 350.75, that would be its temperature of fusion, right? Since it's melting.
Yeah. Good. They say comma, it's melting temperature.
Yeah, the other one would just be like a change.
See, that's the confusing part. How do you know which temperature to pick? Right? If they wouldn't have said it's melting temperature, how would you know to plug into 350?
I don't know. Then it wouldn't work, would it?
Ah. But my way would have. That's a good one.
I'm still on
Okay. Are you ready for 4? The vapor pressure of benzene between 10 and 30 degrees fits the expression log of P slash torr. Remember what the slash unit is. That just means that's the variable unit has to be. Find the enthalpy of vaporization, the normal boiling point. So there's a real strong hint to this in the concept preview. Because they're talking about this liquid vapor boundary. Let me give you a hint. See, they don't want us to use the Clapeyron equation in this number 4, because they're giving us information that it fits this expression. So you're supposed to be using that. So instead of going here and doing concept preview and getting our answer, we're not supposed to go that route. You know, that Clausius-Clapeyron equation. We're not supposed to go that route. We're supposed to use their expression. Now, do you see the problem? dlnp, if we know the function, if we can take the derivative of a function with respect to temperature, we can get del vap h over RT squared. But that function has to be lnp. It's not lnp, it's Log p. Well, how do you turn log into natural log? Remember what we did? Someone figured out. What'd you do? Multiplied log by 2.303, then magically log turns into natural log. So multiply this whole expression through by 2.303, both sides. Then you'll have a natural log expression, right? This whole thing would go in there. Then you'd have a natural log expression. And then since you have the expression, just take the derivative with respect to what? T, and set it equal to del vap h over RT squared. And then just solve for the enthalpy of vaporization. That's how you'd that's how you'd handle part A. So let's just call that equation 1. All right. So just find the derivative with respect to temperature and then solve for del vap h. So when you take that derivative with respect to temperature, what do you end up with on that side?
It's negative 4, negative 1780 pounds at 23.2.
Oh, but don't forget that T isn't on top. That T, it's divided by T. It's divided by T. So you have a number, so that number is just going to go away. That's gone to 0. But here you have another number. Again, don't forget it's times 2.303. But it's divided by t. So the derivative of t to the negative 1 is what? No. There it is, negative 1 over t squared. Take that 2.303 out. Oh, whatever. All right, something like this.
Wait, only that's divided by t, not the whole thing.
I'm just, see what it says? 7.96 minus 1780 over t. And you set that whole thing equal to del vap h over RT squared. So the t squared should cancel on you. What do we say it equals to? Del vap h over RT squared. All right, so your t squareds will end up canceling, and you can solve for del vap h. So let's get caught up, and then we'll get the next one. Did I lose anybody?
What are the units? Is it being Kelvin?
They didn't have. They said,
How do you know what RT?
well, I think, in order for this to work, all I can really say is if you're going to use this expression, P has to be in torr and T has to be in Kelvin to use that expression. And then when you solve for del Vap H, I think R is going to determine it, right?
Which two are you dividing 1780 by? Or you're not?
Just 1780 divided by T. So after you multiply through by 2.303, you just have a number minus a number times T to the negative 1. I think it has to come out in joules.
So do you have the answer for that?
Mm-mm.
It's 34.08 kilojoules per mole.
Yeah, I did that. Right, that's over kilojoules per mole.
Okay. We're good? Number 5. Hint, assume P1 is 1 atmosphere. When benzene freezes, its density changes from 0.879 grams per cubic centimeter. What the hell does that mean? Is that typed up wrong or what? I think you might need a book.
Yeah, you're missing a density.
I think we're missing a density, right? It changes from what to what?
The other density you think is 0.891 grams.
So the liquid is, yeah, we're missing the 0.891. And that's supposed to be the solid. This is the liquid. So enthalpy of fusion is 10.59. Estimate the freezing point of benzene at a new pressure. So they're talking about the solid-liquid boundary, changing the pressure. They give us the enthalpy of fusion. It's fitting in really well for our solid-liquid boundary, or Clapeyron equation. Seems like we're only missing one thing. We're going to solve for, in our, oh, hell, let me write it down. P2 equals P1, enthalpy of fusion, over the change in volume for fusion, natural log T2 or T1. Okay, which one are we going to solve for? Which variable? Yeah, as long as, if you say T2, then P2 has to be what? 1,000 ATM. So it can be either one. You just got to be consistent. So T2 makes sense because it's kind of the logical way to do it. T2, great, and then that means P2 has to be 1,000 ATMs. P1 is 1 ATM. But I would convert to what? Pascals. Be safe. Okay. And they told us enthalpy of fusion. Just be careful. Get it in the right units. How are you going? I think the real trick is finding this guy.
Now, how do you do that? That's what I don't know what to do.
All right. How are you going to find that?
You just find the difference in the densities and then multiply by the molar mass to get the meters, to get meters cubed.
Well, I think we did. And there's a wrong way and there's a right way.
Molar volume.
Yeah. What did I do that was the right way? I don't want to do it the wrong way.
The 1 over the density times the molecular.
I got it into molar mass.
Yeah,
Yes, because that's right. Okay. This, what's kind of hidden here, I think, is this per mole stuff. This is really molar volume.
right.
This is really molar volume. So you really should get this in terms of molar volume. So you could get this guy in terms of molar volume. You pretty much just flip it, right? Because then you'd have cubic centimeters per gram. Get it into cubic meters per gram, but gram isn't molar. So then use molar mass to get it in cubic meters per mole. Do that for each one of these and subtract them. Seems to me you should be able to subtract these two densities and then do the same thing, convert it to cubic meters per mole. I think you would get the same answer because those conversion factors should cancel out. I would think. How did I do it? Now I did each one individually. I found cubic meters per mole for each of these. Then I subtracted. So which one, so when you do get to cubic, don't worry about it. You can see how to get the cubic meters per mole, right? Which one do you subtract? Which from which? It's freezing, so it's liquid to solid, so subtract solid minus liquid, final minus initial. And I think that's what screwed me up when I did this the first time, because I think you end up with a negative sign, if I remember this right. Maybe, maybe not. But anyway, it's freezing, so definitely it's going from liquid to solid. So that means this should be final minus initial. Right? Whether it's positive or negative, that's be. It should be positive, I would think. Almost everything was positive. Okay, so we're good there? Mm-hmm.
For 6.4, how do you find the boiling point?
Oh, we didn't do that. The normal boiling point of benzene. Well, normal boiling point is at, well, normal anything is at what pressure? 1 atm. So if you know what's 1 atm, let's see, what have we found here? We have some half-written expressions here. What I'm thinking is that we use this relationship that they gave us. Since we're not supposed to use our Clausius-Clapeyron, we're not supposed to use liquid vapor Clausius-Clapeyron. We're supposed to be using this expression. So it relates the vapor pressure and the temperature. So if you put in 1 atm, well, I get it in torrs, right? Because this expression's for torrs. Get it in torrs and solve for T, and that'll be your answer in Kelvin. I would say that's the normal boiling point. I think I'm pretty sure that's what they expect. They expect you to use that expression, and not the Clausius-Clapeyron expression. I could be wrong. I don't think so, though. I'm pretty sure that's what they want you to do. Does that make sense?
Mm-hmm.
Shelby, that makes sense? Okay, so for part B, they want to know the normal boiling point. And what you're supposed to do, if we clean that up, it was log of P is 7.96 minus 7.96 minus 1780 all over T. And I didn't write it all, but to use this equation, P has to be in what units? Torr. T has to be in Kelvin. Okay, so this is the vapor pressure. Well, if that's the vapor pressure, here's our boiling point, right? Because that's our phase diagram. So to reach that vapor pressure, that temperature. So it's really the boiling point. Remember, that's the boiling point curve. If you, I know it's kind of confusing, but if you take a look at phase diagram, right, here's our gas-liquid boundary right here. Well, you can call that the gas-liquid boundary, but that's where gas, the line is where gas and liquid are at equilibrium. Well, that's boiling. Things have to be boiling there. So you can call this the boiling point curve if you wanted to. So as you crank up the pressure, look what happens to the boiling point. It keeps going up. Makes sense because the vapor pressure is higher, right? It's going to take more work to get out of there, more effort, more energy. So that pressure, that temperature. So this curve is what they're trying to give us in that expression. Where'd it go? Here. So if we know the pressure, got it, let's solve for T. That's what they want. And P, they said, is normal. Well, 1 atmosphere. But it needs to be in torr, so 760, because a torr is a millimeter of mercury. Okay, then just solve for T. We're out of time. So that gives you, 2 whole homework problems. And 6 really had to do with the concept preview, knowing what a watt was. That's your hint to do 6. And 7 is the Dalton's law kind of idea.